All right, so the next section in chapter 22 is about the Robinson annulation. This is a reaction that still uses enolate chemistry. So really all it is a Michael addition followed by a cyclization. We already saw Michael additions a lot. Followed by an intramolecular Aldol condensation. I'm not super big into the names, but I do use the names a lot, so I want you to know. The most important thing to me is understanding why we're pushing arrows the way we are. So let's start with the first one. With the Michael addition, if you remember back to last week, you have to have some sort of highly stabilized carbanion. Usually it's due to resonance. So in this case, whoops, I skipped ahead. In this case, these protons right here are really acidic because if we have hydroxide around, the resulting conjugate base is resonance stabilized across both carbonyls. Do you remember that from last week? I know it feels like a while ago. And then the next part of a Michael addition is you have to have some sort of alpha beta unsaturated ketone or aldehyde. So I'm just going to use a simple one here. And just like we saw last week, it prefers to attack the beta position. That will push electrons over and up onto the oxygen. Let me zoom out a bit here. That gives us our intermediate that has a negative charge. But right now we're at an enolate. We know that this can tautomerize and will tautomerize back to the keto form. So this will clamp back down. This pi bond will steal a proton back and will convert that enolate up there back to a ketone. And there we go. So this is our Michael addition product. But if we have more hydroxide around, we can keep on going. And in this case, we've got a few options for alpha protons. So let's identify our alpha positions. We could pluck off this proton. We could pluck off one of these protons, could pluck off one of these protons, or we could pluck off one of these protons. But the big thing with these reactions is you need to pluck off alpha protons that are 6 carbons away from another carbonyl group. Does that make sense? Because if we're doing an intermolecular reaction, we like to form 6-membered rings. So now we've got to ask ourselves, which of these alpha positions are 6 carbons away from another carbonyl group? So let's go ahead and zoom in on this and say, all right, I'm going to arbitrarily pick this set of protons, or that proton, I should say. Are there any carbonyls that are 6 carbons away? No. So it's unlikely that it's going to be that one. So I'll erase that. What about this one over here? Nope. Nope. Oh, no. Thanks, Microsoft. All right, so we've eliminated both of those. Neither of those are going to be 6 carbons away. What about this one right here? Nope. All right, that leaves us with our final alpha protons. So I'm going to draw in these alpha protons. And we're just going to go ahead and snag one of these off. And people will say, well, what about the other ones? Don't they get deprotonated too? They do. Under equilibrium conditions, they'll be deprotonated and you have this complex mixture of enolates floating around. But this is the only one that allows you to go in a forward direction. So this is the only arrow I'm going to show. All right. So now we've got to find the carbonyl that's 6 carbons away, and we've got a choice for this one, but we know it's got to be one of the ones on the ring. So I'm just going to pick this lower one right there. It doesn't really matter because it's a symmetric molecule. And this can swing around and do an intramolecular aldol addition. So it's going to attack there. So anytime I do this, I like to keep my original ring static. And then carbon 6, we know must have an O- group coming off of it, right? What I'm going to do is say, all right, this is still carbon 5. Man, my penmanship is getting worse. So let me renumber this. I'm going to zoom in actually. So this is 5 and that's 6 down there. We still have carbon 4 coming off up here. And then we go around to carbon 3. That's still there. Carbon 2 still has the carbonyl on it. So I'm going to label that as carbon 2. And then carbon 1 is now bonded to carbon 6. So I'm going to go ahead and write carbon 1 down here. Does that make sense? Numbering your rings is really important for keeping track of where substituents are located. And for me, I really like to slow down and be careful because before you know it, you're multiple steps in, you made a mistake, you have to go back and erase everything and start over. All right, next step, we still have water around. This is going to grab a proton off of water. We still have these two 6-membered rings. So now I'll show this as OH. I'm not going to worry about numbering now because we're pretty confident with our numbering system. All right. And we've regenerated hydroxide. And if we've got heat, we know we can do the condensation reaction where this is treated as a leaving group. So now the question is which beta protons are likely, or sorry, which alpha protons are likely to be plucked off and eject off that hydroxide as a leaving group. And what I mean by that is we've got a couple options. We've got protons here, here, and here. Do you think it makes sense for the top one? Could be. Definitely. What about this one right here? Doesn't make much sense for that one because it doesn't lead to any sort of extended conjugation. Or it could be one of the red protons down below. So the reality is you might get a mixture. For this one, I will say we haven't really covered this, but typically double bonds in between two ring systems aren't that favorable because then it restricts rotation and flexibility. So for this one, without knowing it, we could say we're going to grab one of these beta protons. So I'm going to swing around, grab this one, clamp down, eject off hydroxide. Oops. And now we've got our alpha beta unsaturated ketone, which is our condensation product. So these reactions tend to overwhelm students. They get really super focused on trying to memorize their way through it. You should not memorize the Robinson annulation. Just try to slow down and justify every single step and why you're doing it. So like up here when I justified picking alpha protons that were 6 carbons away, slow down and take the time to do that. Same thing with identifying the alpha protons for that last step. Identify one that extends the conjugation of the system. That's always going to be your thermodynamic favorite. Yep.
If you do this in a lab, is it a mess? Like, does it impact all different kinds of alpha protons and things, or no?
In this case, like I said, 6-membered rings are highly favorable. So that's going to be preferred due to thermodynamics. And then that last step, double bonds prefer to not be in between 2 rings. That's thermodynamically unfavorable. So this product right here is definitely going to be your major product. You might observe some smaller minor products though as well. Yeah, good question. All right, so that's really it for this chapter, but I like to kind of break things down into small synthesis strategies. So let's do a bit of review. And the first one I like to do is alpha functionalization. And we started out with halogenation. And with halogenation, we said if you've got a ketone or an aldehyde with alpha protons, that you can treat it with acid to make your enol, and then elemental halogen, usually bromine. And that will allow you to install a bromine off of this alpha carbon right here. And we also saw that we can do a variation of this. So I'm going to make a note. With methyl ketones, specifically, you can perform a haloform reaction to get a carboxylic acid. So that was the one we did in lab, right, with bleach and sodium hydroxide. That only works with methyl ketones. If you've got an ethyl ketone or any other type of ketone, it doesn't work very well. So it only works well with methyl ketones. All right, so that was one of the halogenation ones we saw. The other one that we saw was alpha halogenation of a carboxylic acid. This was the Hell-Volhard-Zielinski reaction, which was a mouthful, where you can attach a bromine onto the alpha position. Does anybody remember the reagents that you need for this? What was that? PBr3, phosphorus tribromide, and elemental bromine in step 1. And then step 2, we need to pop off the halogen and get it back to the OH for the carboxylic acid. And that can be done just with water. So this is a relatively straightforward reaction for alpha halogenation of a carboxylic acid. Make sense? All right, we also saw alkylation. We saw that there was actually a few different ways to do this. So I'm just going to stick with the example we did in class, where we've got this cyclic ketone. We've got one set of reagents that will do alpha functionalization on the right-hand side. Meaning we're going to alkylate the more substituted carbon. And then we had an alternate set of conditions where we could favor alkylation on the less substituted side, on the left. Now we need to remember how to do either of these. So let's do the top one first. What should we do if we want to alkylate the more substituted alpha position? Do we want a big bulky base or small base? Small base. So NaH. Should we run this hot or cold? I'd say probably somewhat cold, because we want the more substituted, or sorry, I'm going backwards. This one you would run hot or at room temperature. I'm thinking of the bottom one. The one down below we want to run cold. We don't want the more substituted alkene. So let's do the bottom one now. Do we want a big bulky base? What would the big bulky base be? LDA. And this is the one you want to run cold, so negative 78 degrees Celsius. That's the dry ice acetone. And then step 2 for each of these is going to be your alkyl halide. Your leaving group that looks like that. And it's important to remember this is SN2, so it can't be tertiary, and it shouldn't even be secondary for that matter. Secondary will favor E2. All right, so that was one of our alkylation strategies. We've got a few more, though, that we covered. One was with diethylmalonate. And we saw that we could convert this to an alpha alkylated carboxylic acid. And in order to do this, we needed a strong base. And what sort of base would be most appropriate for this? Can we just use hydroxide? If you remember, we always want to use the base that corresponds to the leaving group on your ester. So step one would be that strong base, in this case ethoxide. Step two would be to treat it with your alkyl halide, which would be Rx. And then, once we've done that, how do we convert our ethyl esters to a carboxylic acid and blow off 1/2 of the molecule? I heard somebody say acid. That'll do the conversion to the carboxylic acid. What about the decarboxylation? Heat. So acid and heat for that last step will help. So when you do this, you blow off CO2. That's important to remember. All right, we saw a variant of this as well. Very similar reaction conditions. So I'll just go ahead and fill this in. But this time, instead of a carboxylic acid, now we can alpha alkylate a ketone and specifically get a methyl ketone out. And just like before, let me clean this up. You're going to blow off CO2 after you convert your ester to a carboxylic acid. Make sense? All right, we saw a few more with beta functionalization so far. We've only seen functionalizing alpha positions for all of these. So let's do beta functionalization. I'll just write it out. And we had to get a little bit creative for beta functionalization. But the key thing was that it really only worked well if you had an alpha beta unsaturated carbonyl, or ketone in this case. So I'm going to go ahead and treat this with RCU, or sorry, this should be R2CU. That was our Gilman reagent. Then water. If you remember, this will allow you to functionalize the beta position of your carbonyl. So now we're not dealing with alpha functionalization. And if you remember, this is an example of a Michael type addition. This works with any stabilized nucleophile. What happens if your nucleophile is too strong? It's not going to attack that beta carbon. Where will it attack instead? It'll attack the carbonyl itself, right? So if we had a Grignard reagent, it would just attack directly into that carbonyl and wouldn't even pay attention to that beta position. So you have to have a weak or a stable nucleophile. All right, so that was our Michael type reactions. We also saw an Aldol. And I'm just going to say cold for this one. We saw with the aldol that you can make a beta hydroxy aldehyde. So again, we're functionalizing this beta position right here. And then what happens if we crank up the heat on this? Yeah, we're going to get an alpha beta unsaturated position. So both of these are technically beta functionalized. And then conversely, we saw a reaction that had esters rather than aldehydes. Just like we saw with the previous reactions, you have to use the ester, or the base that corresponds to the ester. You treat this with water at the end. these ones, you might remember back to our previous notes, but I said if you have a 1,3 dicarbonyl, it's likely going through this sort of reaction pathway, not the aldol reaction pathway. I see a lot of people try to stop here and oxidize it. It's just a lot easier to do the other types of reactions. Does that make sense? So really, these are the main reactions that we covered this term. Like I said, please don't brute force memorize your way through this chapter. It won't work. You'll get overwhelmed and stressed out. Try to just practice your arrow pushing a lot. I do have a summary of reactions on OneNote, so you're welcome to use this as a study aid, but you can see all of the reactions that we covered, including the intramolecular ones. Really, they're just variations off of the Claisen and Aldol reactions and the Michael addition, as well as the Robinson annulation and then the Stork enamine workaround that we saw. If you want a fill-in-the-blank study guide, I pulled this from the study guide, and you can print this off and fill it in as just a study aid. But really, just doing more problems from the textbook is the best way to study for the exam. What I've given you